Hi everyone, welcome to today's session titled Introduction to Anoma for App Developers. My name is Michael and I work on the applications team at Anoma for more than a half a year now. My background is in academia and like before I joined Anoma, I worked in the Solidity ecosystem or Ethereum ecosystem as a Solidity dev for roughly 3.5 years. I developed a modular plugin system and know a few of the pain points of Ethereum app development as well. So let's give people a minute to join before starting. Meanwhile, we will have more sessions in the following weeks in the new year where we show application demos and tutorials, how to write them. However, the session today will be about concepts and how to write intent-centric apps for Anoma and what you need to know about this for doing so. That being said, let's start. The session will be roughly 45 minutes. And in the end, we will have some time for questions. So let's dive into it. First of all, let's briefly discuss what is Anoma actually. So Anoma is a distributed operating system allowing you to build intent-centric applications. What do we mean by operating system? Well, operating systems first and foremost abstract hardware away behind an interface. So that would be your graphic card, your hard drive or a keyboard or your camera. So if you develop an app, let's say on Mac OS, you don't need to know about all these components. You can just use the operating system and write in applications for it. In the case of Anoma, we strive to build a distributed operating system, and this means that we will, this operating system abstracts blockchains, infrastructure like file storage, data availability indexing, and wallets for different ecosystems away, and will provide a unified and smooth environment for developers to build their app in. We will cover a few topics to understand better how Anoma will achieve this, that I will briefly walk over in this overview. So first of all, we will discuss Anoma state model, the Anoma resource machine, then what resources are in detail, what transactions are, and what the application components are and how applications work. And lastly, what services Anoma nodes can provide to users and applications. So let's start with the state model that Anoma uses. The state model behind Anoma is quite unique. Anoma organizes state in atomic units called resources. And below you see a graphic where you see a state space where like 2 slots are empty and the other ones are populated by objects that are resources. So in this case, there are 3 coins, 2 leaves, a potion, and a gear resource. And all these resources, first of all, can contain arbitrary data and are associated with arbitrary logic predicates that kind of describe the behavior. So a coin or a token behaves differently than a leaf resource. And especially when we think about state transitions. So in state transitions, these resources are consumed and created, which is shown in the graphic below, where you see the image of the previous state space and an updated state space on the right-hand side, and a transaction in the middle that takes 2 resources as an input, a coin and a gear in red, which indicates that those are consumed, and a new coin is created. The old resources are consumed and are also crossed out on the right-hand side. So this is the resource model in a nutshell. for this transaction to be valid, all the resources and their logic and the logic they carry must be valid. Otherwise, this is not a valid state transition, which is checked by the Anoma resource machine, besides a few other rules that we will come to later. So yeah, this is the resource model, and we'll compare it to other models on this slide to better understand what this means. So other popular models are the account model, shown in this first column, and the UTXO model that is shown in the second column. On the column on the right, there you see the resource model and the graphic I just showed you. The UTXO model and the resource model are very similar, which you can already see by just looking at the graphics, but we'll also see this in the course of the slide. And yeah, the account model probably is most known because it is used by protocols like Ethereum and Solana and other blockchain protocols, whereas the UTXO model is, for example, used by Bitcoin and Zcash. The resource model is unique to Anoma, and yeah, let's look at the differences. And let's do this by thinking about an example application, for example, a simple token app. So on Ethereum, you would write your contract, maybe an ERC20 token contract, and this contract has state variables that you put inside, and then you deploy it on the blockchain to an address. And then you can call functions inside this contract, for example, to transfer tokens to someone or to just look at the balance of an account. And this is different from the UTXO and resource model. So here, state is explicit, meaning you have to put a mapping of balances in the contract that includes every account and a value associated with each account that represents the balance. So it's explicitly and globally expressed in the smart contract. In contrast to that, the UTXO and the resource model have state represented implicitly. So a balance of a user or an identity in the UTXO and resource model is the set of all unspent transaction outputs that this user owns, and in the resource model of all the resources that this user owns. So the balance is kind of fragmented among all these different objects and local, and in order to read your balance, you have to first aggregate all the objects and then do the sum over them. So like a UTXO can have like more than one unit contained inside, and but to get the total balance you have, you need to sum over all of them to get the total number of coins you own, let's say. So this is quite different. Also, to modify state in Ethereum, you just call, or in the account model, you just call the transfer function. In the other two models, you would consume and create objects. So UTXOs in the Bitcoin or Zcash case, and in Anoma, you would consume and create resources. Another difference is the kind of logic that you can express in your application. So in the account model, you can write arbitrary logic in your smart contract. This is not the case in the UTXO model, the standard one, where every UTXO has the same logic. So there's only a coin logic or a token logic and not more. Whereas in the resource model, you can have, as we already mentioned, associate arbitrary logic with each resource. What does this mean? In the account model, you can have general applications, whereas in the UTXO model, you just can do payments. In the resource model, however, you can have general applications, and moreover, you can also have intent-centric applications, which we'll discuss later in detail what this means. Another important thing is information flow control. In the account model, state is global and everyone can see everyone's balance. So it's very limited, or you could also say you have no real control. In the case of Zcash, you can do shielded payments, which is already great. In the resource model that Anoma uses, you have full information flow control. You can have transparent, shielded, or even private transactions, like fully private if the zero knowledge technology goes to this or arrives at this point. Right. This creates like several advantages that you can make use of. For example, in the resource model, you can also create and consume resources on different controllers. With controllers, we mean things like L1s or L2s, or even 3 friends in a local area network having a very low trust consensus among between them. So yeah, you can consume a resource on one blockchain and create it on another, so they can kind of move between them. And also information flow control. Maybe to give an example, you can have your standard counter application and you create this counter with a value of 0. Then you increment the counter by 1 with in the transparent domain by making a transaction. And in the next transaction, you can decide to increment the counter shielded. And this is just the switch of a flag. So what then happens is that the counter gets incremented from 1 to 2, but only you and the people you want to share it with can see it. External observers will not know that there is a new counter object with a counter value of 2. And then you can also decide to go back into the transparent domain and increment the counter from 2 to 3 and do this in a transparent transaction. Observers will then see that there's a counter with value 3, but they don't know where it originated from. So yeah, that's also quite a cool feature, I would say. So let's take a look at how Anoma does this and what the Anoma resource machine is. So the Anoma resource machine is a virtual machine. You can also call it an intent machine, and it is part of the Anoma protocol. You can think of it like the equivalent to the Ethereum virtual machine for the Anoma protocol. What it does is it creates, composes, and verifies transactions that users send. Transactions can only be executed if they are balanced and valid. That's what the verification ensures. Balanced means that the total quantity or the total number of consumed and created resources of the same kind must be equal. What does this mean? So, like if you consume an apple and create an apple, like there must be equal quantities on both sides. So the delta value must be 0. And to convince the resource machine that it is true, you provided a delta proof. Another property that a transaction must have to be executable is that it must be valid. This means that all created and consumed resources must have valid resource logics, meaning that they are agreeing that this transaction is allowed to happen, giving all the things that happen inside. Also, every resource, for every resource, there must be a check that is valid, that it complies with the life cycle rules, which basically means that a resource must have been created before it is consumed, and some other things that we will briefly discuss later on. Yeah, so this is the Anoma resource machine, and the Anoma engineering team is currently working on 3 resource machine instances: a transparent resource machine that is written in Elixir and Nock, and 2 shielded machines, one in Cairo and one in RISC-0, that that people can use when sending transaction. Currently, we are not working on a private resource machine simply because the zero knowledge technology is not there yet. So fully homomorphic encryption is still not feasible in practice. And but as soon as this is like feasible, we will also add a private resource machine. Okay, so let's dive deeper into what resources are. First, an overview. So we already mentioned that they can have arbitrary data and logic predicates. And they can also be of different kind, in contrast to the UTXO model where you have just one type of object. It's always a coin, and in resource model you can have different objects or different type, like let's say a dollar resource, an apple resource, or a message resource. Those would be different resource kinds. And as mentioned, resources are created and consumed in transactions. Below, the life cycle of a resource is shown. So resources, first of all, the beginning of the life cycle, it doesn't exist. And in a transaction, it is then created. And in another transaction, it is then consumed. There are exceptions to this rule, ephemeral resources, which we'll discuss later, but it's not super important for what we want to cover today. All right, let's look at the state that resources carry. Resource objects have multiple fields, and we will look at 3 for now, the most important ones. So first of all, a quantity, then a label, and a value field. The quantity contains the number of units that this resource represents. So a $10 resource would have a quantity of 10, 2 green apples would have a quantity of 2, and 1 message would have a quantity of 1. Then inside the label field, we can put arbitrary data that describes basically what this resource is about. And this also influences the resource kind. So in the case of a dollar resource, it would be, for example, the symbol, so USD, and who the issuer is, so an address. In the case of an apple, it would be maybe the species, so apple and its color. And in case of a message, it could be the author and the channel ID. So these make or influence the kind of a resource, whereas the value can also contain arbitrary data, but is not influencing the kind. For example, a dollar resource will have an owner that is allowed to spend it. And the owner of the dollar doesn't really change what the dollar is about. It's just another property that this resource has. But it's not influencing the kind. The same for the apple, where we could have a fruitiness value, 80% in this case, or in a message, there would be some text that this message is associated with. Next, we can look at another field another piece of information associated with the resource, the logic function. So the logic function is a Boolean valued function that returns true or false and expresses certain predicates and conditions that must be fulfilled in order to create or consume a resource. For example, a dollar would have a logic that ensures that it can only be transferred to someone else if the current owner signs a message and authorizes this explicitly. A green apple, for example, can only be eaten if its fruitiness is high enough. And a message resource can only be edited by its author. And in these logic functions, you can check data that is part of the resource itself, for example, the owner field, or data present in other resources that are also part of this transaction object. So resources can also check each other and make sure certain properties are met. Right, so those are resource logics. The resource object contains more fields besides those 4 that we just discussed, so logic, label, value, and quantity. The object, the next field in the object would be the nonce, which is basically a number that ensures that this resource is unique. A randomness seed, which you can use to derive pseudo-randomness, which something an application might need. A nullifier key commitment, long word. This is important in the shielded case, and when you consume a resource, there is a nullifier mechanism or nullification mechanism we'll briefly touch later on. However, this is important for this mechanism. And then there's an ephemeral flag that can be true or false. And this flag basically says that this resource can only exist over the course of a transaction, which is something you need under special situations, which we'll also briefly touch later on. Right, so this is the resource object, and you can compute certain other values or components from this object. One is the kind we already discussed, which is the hash of the logic and the label. And this expresses the fungibility of a resource and with which other resources you can interchange it. For example, $1 and an apple have different kinds. They are not interchangeable, whereas one Apple resource and another one Apple resource have the same kind. And this would allow you to merge them into a 2 Apple resource if the logics would allow you that. This is used in the ARM or Anoma resource machine balance check, but also to index resources, which is relevant for applications. So what you might want to do is fetch all tokens that you own, and then you would filter all existing resources by kind, and then by who is the owner. Right, so creation and consumption, what needs to happen here? If you create a resource, what essentially happens is that in the transaction object, you put in commitment, which is the hash of the resource object itself. And when this transaction gets executed, you put this commitment into a commitment tree, which is a Merkle tree that lives on the controller. This resource is created on a blockchain. There is a Merkle tree, and knowing a resource, you can check in this Merkle tree if this resource was already created by looking up the commitment. Similarly, when consuming a resource, you compute a nullifier, which is obtained by hashing a resource and a secret nullifier key. This nullifier key is important in the shielded case, not in the transparent case. However, once you have computed this nullifier, you add it to a nullifier set that is maintained on the controller, and this also allows people to check whether a resource is already consumed or not. The nullifier key, by the way, has to match the resource, the field in the resource that we discussed, the nullifier key commitment, and only then this would be a valid consumption. Right, so this is creation and consumption, and ephemeral resources are resources that are indicated by the ephemeral flag in the resource being set to true. And if this is the case, you don't need to create this resource in order to consume it. And also you don't need to add the commitment to the commitment tree or the nullifier to the nullifier set. This is important when you, for example, initially create resources or you want to finally consume resources. You can think of it as like minting and burning resources. So let's assume there is the Genesis block and no resource exists yet, not a single one. And you want to create 10 apples. However, there are no apples that you can consume, and in this case, you will create 10 ephemeral apples that only exist for this transaction or over the course of this transaction. You make them up from thin air, and then this transaction would be balanced. The same will happen if you want to finally or permanently delete or destroy apples. You would need to consume 10 apples, and in order to balance this transaction, you would create 10 ephemeral apples. This is useful for these scenarios I just described, and has to be explicitly has to be allowed explicitly in the resource logics. And another scenario in which this is useful is if you want to express advanced intents that add constraints to a transaction and over other resources, and this intent would only live over the course of the transaction. However, this is an advanced topic that we will not discuss yet. Okay, so let's look at transactions in more detail. Right, so transaction can be balanced if they contain equal quantities on both sides, so on the consumption and creation side, and if there are like the same number of resources of some kind, then this is a balanced transaction that can be executed if all other criteria are met. So such a balanced transaction would be sent to a transaction mempool where an executing node can pick this transaction up, verify it, and put it in a block. In contrast to that, you can also create unbalanced transactions where certain resources are not balanced yet. And this is what is actually called an intent. So an intent is not more than just an unbalanced transaction that misses some parts. And these missing parts usually come from counterparties that have matching intents. So we will have like look at a few examples in the next slide. Next slides. And what needs to happen is that you or someone identifies these matching unbalanced transactions and composes them into one so that they are actually balanced, and that the rules above apply, and that it can be executed. This is the job of solvers, which look into intent pools and try to find matching intents and optimal solutions for advanced counterparty discovery problems. Right. Let's do an exercise and see if we can tell which transaction is balanced and which is not. So every row in this table is a transaction in which some resources are consumed and others are created. And your job is to think if these are balanced or not. Give it a few seconds for you to think before I show the solution. Right, so let's start with the first example. So here we have 2 green apples on the left side and 2 on the right side. This is a balanced transaction. Here we have 2 apples, a 2 apple resource, and 2 resources with 1 apple each. This is also balanced. Here we have an apple and a shell. Those are of different kind, and this is not balanced. In this example, we have mismatching quantities. So we have 2 apples on the left side and 1 apple on the right side, 1 shell on the left side, 2 on the right side. This is also not balanced. Here we have a red apple suddenly. This is a different kind than the green apple. So you are not allowed to add these 2. So this is also not a balanced transaction. And here we have more complicated transaction, but overall the quantities of the same kinds match, and this is also a balanced transaction. Let's look at an the example of a transfer. So let's say Alice has owns an apple and wants to give it to Bob. And the transaction that corresponds to this statement looks like this. Alice consumes an apple, and with the curly braces, we indicate that she's the owner of this apple. And in this transaction, one apple is created for Bob. And looking at this transaction, we see that it's already balanced. And this means if the resource logics are fine and all the checks are met, then this can be executed straight away. So here, no counterparty discovery is needed, no solvers are needed. It can just be executed. And after execution, what then has happened is that Alice has given her apple to Bob. So the main point here is that for some transactions, you don't need to have a counterparty. You can just do it on your own. This is different in the next example, where we do a swap. So Alice wants to give her apple for a baguette, and Bob, on the other hand, wants to give his baguette for an apple. So those two are unbalanced transactions individually. If you look at them, here's Alice's intent: consume one apple and receive or create one baguette. And Bob's intent is the opposite. And coincidentally, those two intents match. And after composing both transactions into one, this becomes a balanced transaction. So this is shown here in the third table, where we see all the resources on the left-hand side that are consumed. So one apple of Alice and one baguette of Bob, and then one apple is created for Bob and one baguette for Alice. So, and if this transaction is executed, what then happens is that Alice and Bob have effectively swapped their items with each other. And yeah, this is a very simple intent, a very basic one that is so simple that it doesn't require counterparty discovery really. If Bob and Alice know each other, they can just do and settle this transaction themselves by combining or composing their intent. So this is not really a complex solving problem. However, for more complicated intents where you also want to express optionality or weights, what you prefer more, or you want to have as much or as many baguettes for your apple than possible, this is where you would ask a solver to find an optimal solution for you. And these are running algorithms to solve constraint satisfaction problems, and then can provide you with a good solution. Let's look at the transaction object in detail, what it actually contains. So there are 4 fields. There is a roots field in which the state roots of the controller are put that are required to verify that the resources that are created and consumed already existed or didn't exist before. Then there is an action field that contain a list of actions in which actually the resources are created and consumed. We'll see this in a bit. And the delta value we were discussing, and that should be 0 for a transaction to be balanced, and a proof that this delta value is correct. So the action object, on the other hand, now really contains the commitments and nullifiers of the created and consumed resources in this transaction or in this action. A list of proofs proving that all the resource logics are satisfied, and also that the creation and consumption complies with the resource machine rules. And the last field is a field to put arbitrary data inside. It's called app data. And this is the place where you would put signed messages, let's say by the owner of a token, that approves that this resource can be spent and someone else can receive created resource. But we don't need to know this in detail yet. Right, so lastly, we can look, or like, there's another section that we can now look at applications and what the components of applications are. This is shown in this diagram, where at the top we have a user that interacts with an interface that is then interacting with a backend, and we have three components being part of the backend and interface. In the backend, we have the model, which is constituted by the resources and logic functions that are associated with an application. And in the interface, we have a view component, which projects data out of these resources. This is why they are called, right? The functions that are doing this are called projection functions. And we have a controller component that allows the user to create transactions, to do state transitions. So let's look at this full cycle. And yeah, obviously this is the model view controller design pattern for user interfaces that we see here. Let's start with the model. Let's say we have some state that exists, and in a token application, and the user wants to know his current balance. So the user would call a projection function in the interface that sums over all resources that are associated with this token, and then calculate the current balance that the user owns. And with this information, the user could then call a transaction function, maybe like to transfer or to swap a token with someone else. This would create transaction object depending on if it is unbalanced or balanced. Different things need to happen now. If it is unbalanced, you need to find a counterparty. If it is balanced, you can execute it straight away. And in this case, the state is transitioned. The resources are consumed and created, and the balance would then be updated. So this is the flow that an application state change would entail. So let's look at the components in detail. The application backend basically is constituted by all resources related to this application. In the case of a token, this would be the token resources, but you can also think of a messenger application where you would probably have messages, some channels, and permission resources. So multiple different kinds of resources that make up your application. And your application state would then be all the data contained in these resources, and the application logic would be all the logic functions and the predicates inside that determine which state transitions are allowed to happen in this application. So you can kind of think about all these resources as the business logic of your application. The interface, on the other hand, contains transaction functions, as we already discussed. This is how the transfer function would look like. It would receive a resource and a receiver as an input argument and output a transaction. And it would require some executing node or block producer to actually execute this transaction. So you need this service from an external node, or you are running a node yourself. In the case of an unbalanced transaction, like the swap function we discussed, the input would be the resource or resources you want to give and the resources that you want. maybe more parameters and more complex data structures indicating your preferences and optionality and whatever you want to think about. And yeah, but the output would still be a transaction object. In order for this to become balanced, you would require the service of a solver finding a counterparty for you if you cannot find it yourself. The read interface that we mentioned, consists of projection functions that aggregate data of multiple resources. So there would be a balance function that takes all token resources that you own as an input and gives you back the total balance that you own of this token. Another example would be a chat history function that receives all messages of a channel and gives you a list of strings that is basically your chat history. And for this to work, you need to track all the unspent resources, meaning all the resources that are currently created and not yet consumed, to really calculate the right balance or have the right chat history. And either you can be online all the time to not miss a resource that you might receive or that might be related to your messenger app, or you could ask an indexer to provide the service to you. So this indexer would track and filter resources relevant for you or your application and give them to you so that you can put them in your function. So what we already see here that you often need services from other node, and that's the last topic we will cover in this session, services, and how these work. So in the Anoma network or in Anoma protocol, nodes participating can provide different services to each other or applications and users of applications. Examples would be elementary services, for example, storage provisioning. Let's say you have an intent that is quite advanced and you want it to be around for long enough time so that eventually when a counterparty has a matching intent, it can be settled. So you say, please store this intent for me for at least 1 week. And here's a compensation for this. Or please store my movie, 1 gigabyte movie, on at least 2 hard drives or at least 2 storage providers. And you would maybe check that this is really that this data is really available and require proofs for this. Another service would be provisioning of bandwidth, maybe for your intent to reach all participants in the networks, you require nodes to gossip it around or route it to the right peers. And this is an elementary service you can think of. Also computation services, maybe to compute a very complicated zero-knowledge proof, but also sequencing or ordering of transactions. At some point, you want your transaction to be executed, and maybe you don't need it to be executed right now, but at least within 1 week or in the next day, you want it to be executed, and that would be also a service to some node can provide to you to put it in a block. Then you can think of advanced services that are like a combination or composition of these services above. We already touched indexing and filtering of resources, for example, by kind and owner. And you're interested in your tokens of a certain kind that you own. And then you want someone to store these resource objects and send them to you if you need them, or your application users. Another service would be solving of intents and finding optimal matches which is something that we all know from CowSwap and other intent protocols. And here you can, the job of a solver is to find optimal matches and, for example, also across different chains and different layers. Right. So these would be solving and indexing services that Anoma applications would find useful and that nodes in the networks can provide to each other. Right. With this, we come to the end of this session. I want to highlight what this talk was about and summarize it. So I hope you learned about intent-centric apps and how they function on a high level, how Anoma peer-to-peer nodes can provide different services to applications. We mentioned indexing, solving, and sequencing. And we also briefly touched that resources can be created on one chain or consumed on one chain and created on another chain, so that you can have cross-chain transactions and different things happening on different settlement layers. Right, so we hope that it gets a bit clear now how Anoma is really a distributed operating system and provides you with an environment that alleviates you of developing and building and operating all this infrastructure yourself. With this being said, I think we have some time for questions. I will open the chat to see if there's something. Let's give it a few minutes for people to write their question. Okay. If this is not the case at the moment, then we are happy to answer your questions in the Discord. Also, brief mention that, there are more sessions coming. The next sessions will be more focused on example applications. We'll start with the simple hello world, then maybe a counter or some rock, paper, scissors game, and also a token application, which we call Kudos. All right, then thanks for joining the session. Have a great day, enjoy the Christmas holidays, and see you in the next session. Bye-bye.